Greetings all. This screencast is about the opening section in chapter 16 on solutions. You can see in this picture here what you should not do or what could go wrong if you want a bigger basement. In any case, not to dismiss the tragedy lightly, sinkholes can often occur in Missouri almost as frequently as in Florida and Alabama and Texas because of the kind of ground underneath our soil. There's a lot of limestone that the state of Missouri rests on, especially because of the Missouri and the Mississippi River basins. And this limestone can be leached away or dissolved away by groundwater, sometimes leaving behind large openings or cavities like this that eventually give way. And this actually happened here in Missouri back in 2006, as you can see. So there are key words here about dissolving and the solution process. What do we mean by them? The first question we're going to ask is, well, what factors determine the rate at which a substance dissolves? Dissolving, of course, is when something, we call that the solute, is put into something larger and disappears into it, and that's called the solvent. And technically, your solute can be a solid or a liquid or a gas, and your solvent can be a solid or a liquid or a gas. For example, if you were to try to dissolve a solid metal in another solid metal, you are creating what is called an alloy of a mixture of different metals, like bronze or pewter or brass. In any case, the solute goes in the solvent. The solute is usually the smaller quantity, the solvent the larger quantity. Now, what factors affect the rate, the speed at which a substance is going to dissolve? Well, if you remember anything about rates from physics, a rate is something divided by time. Velocity, for example, would be distance divided by time. Acceleration would be velocity divided by time. The rate at which you eat food during the day might be not just your 3 meals, but your number of snacks divided by time, 24 hours. We could talk about the rate of cars going down the interstate, the number of cars divided by a period of time, like per minute or per hour or per day. So the rate is something divided by time. You have a unit of time in the denominator. And various things can make that go faster or go slower. Just like the rate in which cars go down the interstate might be affected by the time of day, whether it's rush hour or not, and it might be affected by weather conditions, whether it's icy or not. So the three factors that can affect the rate in which something will dissolve depends on stirring, temperature, and the surface area of the particles. Now, this kind of messiness right here, which bothers somebody like me, is a function of uploading this PowerPoint into Notability, and I have no control over that. So let's look at these in each in turn. For example, if you have a glass of iced tea, and you can see the ice right there, and you want it to be sweetened iced tea, especially if you're from the South, you could put an ice cube in there. Now, that ice cube does not have an awful lot of surface area. It's hardened, and it'll take a while for that to dissolve on its own. However, if you were to grind that up or pulverize it, or if you were just to use granulated sugar that comes that way in the first place, Now when you stir it up, it's going to dissolve much more rapidly because there's way more surface area in the granulated sugar than there is in the sugar cube. So surface area is going to be a big deal. And of course, the greater the surface area, the more collisions you're going to have between the particles of water, molecules, and the grains of sugar, which are also molecules. If you were dissolving salt in water, your particles would be ions of sodium and chlorine instead of molecules. Now, another factor, of course, is to heat it up. Over here, if the temperature gets higher, things are going to dissolve an awful lot faster because now your particles, be they ions or molecules, are going to be moving around much more rapidly than they were at the lower temperature. Because remember, temperature is a measure of the average kinetic energy. You can designate kinetic energy E sub K, because there's lots and lots of different kinds of energies, or a lot of times books will just say KE for kinetic energy. Stirring also works, and in AP chemistry, and sometimes in other chemistry classes, we will use this magnetic stirrer. There is a magnet inside the black base of this machine that spins around, and then we put a stirring bar. Usually it's a white Teflon coated stirring bar. You can barely see it in the shade right here. And that magnet will spin because the magnet inside here is being made to spin electrically. And as a result, the stirring bar is going to stir up the solution. And again, this speeds up the dissolving process because it increases the contact that the liquid is going to have with the solute. It causes basically way more collisions. Temperature, of course, can increase the rate of dissolving, as mentioned, because if you remember, the formula for kinetic energy is 1/2 mass times the velocity squared. So if you speed up the particles by increasing their temperature, they now have more kinetic energy, and therefore you're going to increase the number of collisions because they're moving faster and banging into each other more frequently. Remember, temperature is a measure of the average kinetic energy of your particles. Here's another way to increase the surface area, and that is by grinding it up. Here you have a mortar, here you have a pestle. And you can grind up the solid, that pulverizes it, that smashes it up, that increases the amount of surface area because it decreases the size of the grains of the solute. All right, solubility. How is solubility usually expressed? Well, we can talk about a saturated solution. A saturated solution means that a given temperature and a given pressure, if we're talking about gases, the volume of our solvent can reach a limit in terms of how much solute can be dissolved in it. If I have a glass of ice water or tea or something like that, and I keep putting sugar in there, I can't add sugar indefinitely. I can add some sugar and stir it up and it'll dissolve, and add some more sugar and stir it up and it'll dissolve. But at some point, I can't add any more sugar. And at that point, the solution is now saturated. And we can talk about what is the maximum concentration for any given solvent when you put a given solute into it. Now, up until the point it's saturated, we say that it is unsaturated, which means that there is room for more. Interestingly enough, you can have a supersaturated solution that occurs when you add more solute than you ought to be able to add to the solvent. But there's a sneaky way to make this happen, which will be talked about a little bit later. Now, We have to remember that the process of dissolving something is not a chemical change, it is a physical change. And when you have a physical change, and we add solute to the solvent, at a certain point, we reach equilibrium. And we designate equilibrium with this arrow that goes both directions. Sometimes you're going to see it designated like this. Sometimes you'll see it look like this. But this means you've reached equilibrium. And there are two kinds of equilibrium. There is physical equilibrium, like in this case, but there is also chemical equilibrium, which you're going to spend a lot of time talking about. And that's when your reactants are at equilibrium with your products, which means your reactants are turning into products at the same time that your products are turning into reactants. Now, that may be a new idea because you're used to reactants going all the way to the right and turning into all products. So you end up with 0 reactants and all products. But that's an unusual situation. It's not that unusual. But this is what happens when one of your products is a gas. You may remember this. Or when one of your products is a precipitate. Or when one of your products is a molecule with a very, very strong bond like water. Or a weak acid. Or a weak base, which we'll be talking about later. When you produce one of these things, the reaction will go all the way to the right. Because when you have a gas, your gas leaves and it's gone. It doesn't hang around for the reaction to revert backwards again. When you have a precipitate, it goes to the bottom of the beaker or the test tube and doesn't hang around. So the reverse reaction going to the left can happen. And when you have a molecule with a really, really strong bond, like water, a bond between the oxygen and the hydrogens, as well as the hydrogen bond between the water molecules, that does not like to go back to the left. So that's a chemical equilibrium, and that's a preview of chapters to come. But in physical equilibrium, you have the dissolving process, which always goes to the right. You have the precipitation process, which goes to the left. And those little boxes are because Notability couldn't handle the coding in the PowerPoint. And as a result, you have the production of solution and the production of solid going on at the same time, in the same place, at the same rate. So you might not even see any changes at all, but it's going on at the molecular level, the particle level, where solids are going up into solution, and we call that solvation. Meanwhile, particles that are in solution are precipitating out, and we call that precipitation or crystallization. And they're going on in both directions at the same time for this particular temperature. So the solvation process, not to be confused with salvation in Bible class or in life, solvation is the surrounding of your crystal particles with your solvent. Usually the solvation process involves water. And we could call that hydration then. Now, when we use the word solubility, we might say, how can I know whether something is soluble or not? Well, interestingly enough, this is not an either-or situation. We actually define roughly a substance is to be soluble when more than a gram of the solute can dissolve in 100 grams of water. Now we say something is insoluble when less than 1/10 of a gram can dissolve in 100 grams of water. And that seems kind of weird because, yes, there is some solubility happening, but it doesn't pass our threshold. You might say, well, is this threshold of 1 gram and 1/10 of a gram somewhat arbitrary? And it's not exactly arbitrary because it turns out that most substances that are soluble actually dissolve at greater than 1 gram per 100 grams of water. And most substances that we call insoluble are actually less than 1/10 of a gram per 100 grams of water when they dissolve. There are a few in the middle. God always has these weird little exceptions to these oversimplified rules that we as human beings and scientists try to create. So, as a rule of thumb, this works very well. But there are some substances that are partially soluble, which means that somewhere between 1/10 and 1 gram of that solute will dissolve in 100 grams of water. Those are good benchmarks to remember. Now, for dissolving a liquid in a liquid, sometimes the two liquids can dissolve in each other and in any ratio we want. For example, alcohol can dissolve in water in any ratio. You can have 1% alcohol dissolving in and have 99% water in the solution. You can have 99% alcohol and only 1% of water. This is certainly true in alcoholic beverages, which run the entire gamut here. So in this particular case, we say the two liquids are miscible. Two liquids are immiscible, and this is, by the way, only true for liquids. We're not talking about the solute being a solid or a gas. They're immiscible if they cannot dissolve in each other. And some examples would be motor oil in water, vinegar in water, and vegetable oil in water. Now, vinegar can dissolve to some extent in water. You can dilute the vinegar. You do that in cooking because vinegar contains acetic acid, and acetic acid is a polar molecule. And of course, water is polar, so like dissolves like. But vinegar and vegetable oil don't dissolve in each other very well at all, just like water and vegetable oil don't dissolve in each other. Vinegar is already a water solution. All right, factors affecting solubility. We're going to see that temperature is a very important factor that determines just how much a solid or a liquid or a gas can dissolve in a solvent. But pressure is a factor only when we talk about gases, not about liquids or solids. And you know from previous experience in the gas laws that gases are very susceptible to changes, not just in temperature, but also changes in pressure. Liquids and solids, for the most part, are not compressible, so pressure is not going to affect their solubility much at all. So if you think about a can of soda, you would all recognize that temperature is going to affect the gases that might be dissolved in that solid. It's not a can of soda, there's no gases dissolved in there. And those gases are actually trapped in this head space up here. There's a little bit of space where you have gas under pressure. And so because it's under pressure, some of that gas can escape and go down, or I shouldn't say escape, but will be pushed down into the sugar water solution. And some of the gas that's trapped in solution will go up into the headspace, and so you're at equilibrium in that situation as long as it is sealed at the top. But when you pop that lid and open it up to the atmosphere, then all of a sudden a lot of that gas is going to escape. And as the gas escapes, you're going to reach a new equilibrium, which has very, very little gas dissolved in the soda. And you all know the name for a soda in which the gas has escaped. You say that the soda is flat, and because the gas has escaped and there's very little gas left trapped in the soda. We should also mention that if you have one can of soda that's very, very cold, and I'm going to peek ahead, nope, one can of soda that's very cold, and you pop the lid, and not only are the gases going to escape, but the temperature is going to go up. And when the temperature goes up, less and less gas can be dissolved in the soda as well. And so what's actually going on is the carbonation or the carbonic acid that created that situation is going to decompose into carbon dioxide, and water. And you should know that anytime you have H2CO3 as a product in a double displacement reaction, that you further decompose the carbonic acid into water and carbon dioxide. And the water is a liquid, and it dilutes the soda. The carbon dioxide is a gas, and it escapes the soda. So not only does the soda taste flat as it reaches room temperature, but also tastes a little bit more watery. In other words, it tastes a little bit more dilute because you have added a little bit of water to that soda. So the more pressure, the more gas you can dissolve in the soda, and more gases are going to dissolve in cold water than in warm water, because warm water means all of your solvent particles have a lot more energy, but also all of your gas particles have a lot more energy. And therefore, they have a lot more energy and are able to escape whatever intermolecular forces of attraction there might be between the gases and the soda. And they can break through the surface tension at the top of the soda, and now they can escape into the atmosphere. They are now free from those intermolecular forces, and so there's less gas dissolved in the soda. You also know that if you're somebody who likes to fish, you're much more likely to find the fish where the water is cold, because there's also more dissolved oxygen in the cold water than there would be in warm water. And the fish, of course, we're going to prefer, where there might be more oxygen. What would make the water colder in some places than other places? It could be in the shade. There could be a spring nearby. It could be extra deep. And that's a good place to put your hook. Now, in Yellowstone, where I've been many times, you have the super hot water due to geothermal activity underneath. And that super hot water will have a very, very high concentration of dissolved salts in it, such as calcium carbonate. And then when that hot water comes to the surface and is exposed to the cooler atmosphere, you can see that it'll go from a place of high concentration where it's hot, and as the water cools down, it's going to leave behind all of these deposits of calcium carbonate and other minerals as it settles out of solution. And you can go through Yellowstone, for example, and see lots and lots of these features in Yellowstone. These minerals are much, much less soluble in cooler and room temperature water than they are at the super hot water. Now, if we look at this graph of solubility of water per 100 grams, which is how we usually rank solubility, you can see that as the temperature gets greater and greater, most of your salts become more and more soluble. Sodium nitrate is very soluble because more than 1 gram of it will dissolve per 100 grams of water. Potassium bromide is very soluble. Potassium nitrate is very interesting. It's not linear at all, but it exponentially increases as it gets warmer and warmer. Interestingly enough, table salt, sodium chloride, is almost flatline. It barely increases in solubility as the temperature goes up. Ocean water, by the way, has an average solubility down here of about 3.5 grams of salt per 100 grams of water. It's about 3.5% salt water. But of course, that's going to vary greatly from ocean to ocean and from place to place within an ocean based upon temperature. For example, if you're near the Arctic Ocean or the Southern Ocean by Antarctica, less solubility of salts because it's so much colder. Also, if the ocean happens to be near the mouth of a river or near melting icebergs, it's going to be cooler there, and that's going to affect the solubility. And believe it or not, you've got some weird salts like ytterbium sulfate that the solubility actually decreases as the water gets warmer. Now, if you heat your solvent up to a high temperature, let's say water, and make sure the water is very, very pure, no impurities, and that your container is very, very clean, a very, very clean beaker, which means you don't want to use a beaker cleaned by a student. That's a joke. You can add an awful lot of salt. Typically, we like to add a very soluble salt called sodium acetate. And when we add this salt at a very, very high temperature, we can dissolve a lot of it in the hot water. And then as we let the water cool, interestingly enough, this salt will stay dissolved. And now my solution becomes supersaturated. It has way more salt in it than it would normally have if I just tried to dissolve it in at that particular temperature. But then as soon as I add a seed crystal, it'll immediately begin to crystallize around that seed crystal. And so this is an example of a supersaturated solution. It's clear, and of course the temperature here is very, very high. We can begin to let it cool, and then as soon as we add a crystal, it's going to rapidly crystallize until the entire solution over here becomes solid. Now it's also possible to have a flat surface and to take a flask of supersaturated solution, and let's make this an Erlenmeyer flask, and it's saturated. If we tip this over and begin to pour it, it will immediately begin to crystallize. And I've had a situation where as I'm pouring the supersaturated solution of sodium acetate on paper, it crystallized so fast, it crystallized up the pouring and into the flask before I could finish. And I believe you will have a video that you can watch of this process going on. Besides a graph, you can also see a chart of solubilities and see that most of these solubilities increase as you go from left to right in temperature for solids, but the opposite is true for gases down here. Solubility becomes less until when you reach boiling water, there are no gases at all left in the water. No dissolved gases. And we already mentioned that pressure has little effect on solids and liquids, but does affect the solubility of a gas. And that is actually called Henry's law. Henry's law says that the solubility is proportional to the pressure. And we can therefore say solubility is going to equal some constant times pressure when we add a proportionality constant. And we can look up what that proportionality constant is for different gases. And there would be a chart for carbon dioxide or oxygen or nitrogen. So just like you did with the gas laws, if I have one solubility at one pressure for a gas, I'm going to have a different solubility at a different pressure. So I can solve this first equation. K is going to equal S1 over P1. And K over here is going to equal S2 over P2. And now I can use a transitive property of equality. If A equals B and B equals C, then A equals C, and that's what you have right here. That ends this screencast.